Out in the hall, they're doing undergraduate research poster
Oh, okay,
presentations.
cool, cool.
So I don't know if that starts at 3 or 4. I'm not sure.
Okay, is this class involved in that?
No, no.
Oh, okay.
No, this
It'll
is
just be noisy, but I only have
It'd
an
just
hour
be,
to
yeah,
give.
but I think
Oh,
it
3 to 4.
should
Yeah,
be
well,
fine.
whatever.
Yeah.
It'll test their ability to filter out background information.
Yeah. I think it shouldn't affect us too much. All right, I'll go ahead and
Sure.
make announcements. Okay, guys. So we have Dr. Brian Gold from the College of Medicine here with us today. He's going to be talking about MRIs and other imaging. So we're having our annual field trip to the MRI facility. Don't worry, you don't have to drive anywhere. We're just going to be walking across the street over to the Markey Cancer Center. You do need to be on time, especially the Wednesday and Friday labs, because we'll be leaving at exactly like 1 o'clock for those 2 labs to go over to the facility. Now you do have a short activity that's looking at some MRI data and kind of interpreting that data. It's something that you guys can do as a group and turn it in as a lab group. This will be your last lab, so if you want to make sure you get your lab partner's contact information or anything, you can do that. We will have one more lecture next week. It'll be on human research ethics. So it is a topic that is kind of relevant to a lot of you if you're planning to go to med school or other professional schools. It's a very relevant topic. So we'll talk a little bit about that. It's a pretty heavy lecture, but that will be on the final. Final is same format as the midterm, open note, but you can only use the notes that you've printed out and done for classes. So any questions? And you can ask me questions during lab this week. So, all right, I'll let Dr. Gold get started.
Okay, can you hear me okay? All right, well, I just learned a lot about your class. I learned your schedule. I learned what's going on in the class. I learned about future lectures. It's all coming to an end, right? It's all coming to an end very soon. And tomorrow, I guess, or whenever your next lab is, you're going to be visiting the MRI Center. I'm a co-director of that center, and you'll meet the other co-director who's a physicist. And so he really runs the day-to-day operations and can answer any questions about how the physics of fMRI work. We'll talk a tiny bit about that today, but not very much. So it's pretty informal. If you want to ask questions, just raise your hand. There's no problem at all. If you want to email me on something, I didn't put my email up here, but you can Google me and send me an email question as well. So I'm going to go through now and talk about this. So this is an overview of the lecture you're going to be hearing today. So these are the main kind of sections that we'll discuss. We'll talk a little bit about how we learned about brain function before MRI was around. We'll talk about a little bit of the background of MRI, some of the basics of functional MRI, what has it taught us about brain function, and then what are the limitations, okay? All right, so this is an example of how we learned about the brain and its function before we had imaging techniques. So this is a famous case. Has anyone heard of Phineas Gage? Heard of this case, probably in psychology? So it's a very interesting case because it was a railway paving accident, and the tamping iron, the rod, flew up and got stuck behind his left eye and through his frontal part of his brain. Okay? So he, for most of the rest of his life, see if this works here, yeah. So he was in a carnival, and he had that eye removed, and he carried around this tamping iron and made money that way. The interesting thing about it was that we learned a little bit about brain function from it, because before he had this accident, he was described to be very, very careful, very on time, etc. And then after the accident, he was described to be more profane and not obeying rules and having a lot of behavioral problems. So it was some of the first evidence that there's parts of the brain that are assigned to different functions, in this case, personality. Before that, all we knew is by people touching our heads, right? Phrenology, which you probably heard about, and thinking that a part of your skull was devoted to a particular kind of function. This was saying, no, it's really about the brain. So there are other kinds of cases where we learned about brain function before MRI was around, and it was often related to stroke. Okay, so these are two of the famous cases of stroke that became named for kinds of strokes today based on their founders. So Paul Broca was a French neurologist, and he saw a patient and then other patients that had difficulty expressing speech. So the problem wasn't in moving their mouth or tongue, it was actually just in getting information, language out. When that person came to autopsy, they were found to have a lesion in this area here, what we now call Broca's area, after him. Okay, some years later, a German neurologist named Karl Wernicke, he saw patients that had sort of the opposite problem. They could express themselves fluently, but they couldn't understand what others were saying to them. So that became became known as a Wernicke's aphasia. So now we have Broca's aphasia and Wernicke's aphasia. Now, what I'm showing here in these activations is not actually what was sort of seen at that time. At that time, there was only pathology, right? There was only histology. So what I'm showing is a more modern fMRI, functional data that we'll talk about here, just to show you where these regions are. But just so you know, there was no MRI back then, and these were named based on the pathology, okay? All right, any questions so far? If not, we'll move on to the next section. So what are the limitations of lesion models? It can only be really studied at autopsy, so you're looking at the brain that is dead, it's not alive. Lesions don't obey anatomical boundaries, so we want to sort of say that a brain region is devoted to a process, but we can't do that with a lesion because it's messy, right? It goes across multiple regions. So we don't know exactly where our location is for our function. And then lesion models don't tell us about connected circuitry, right? They don't tell us how the white matter connects different parts of the brain, and that if there's damage, you're really disrupting a network, not just a region. So it became, we'll see with MRI, able to study networks in the brain, not only single regions. Okay. So let's look at some examples here of imaging that came around. So a CAT scan, or actually we should just call it CT scan, a computed tomography, is a scan that came around in the 70s. And as you can see from the CAT scan, it is very good at imaging bone. What we see around the surface here is bone, it's white. So it's basically like using x-rays. So it's high-powered light that is, instead of being 2D like an x-ray, it's 3D, and it's computerized. So you can look at the brain in any orientation you want. This really became common use in the 1970s. You can see that in addition to imaging the bone well, what we have is we have some structure we can see inside the brain. It's just not very, the resolution isn't so good because this technique is not capable of great resolution. Okay, so the reason that we see bone well is just because it's really about imaging, electron density, and calcium has a lot of electrons. So we then look over here to the other side, and we see an image in about the same plane, and this is an MRI scan. So MRI was developed in the 60s and 70s, but it wasn't until the 80s that it became used in hospitals and clinics. And actually our MRI center here was among the first research centers to get an MRI in around 1984. Okay, so what I want you to notice is, first of all, with MRI, it's not really about imaging bone. What you see here on the surface here isn't bone, it's fat. So MRI is really good at measuring water, and it can be water in fat or straight water or water that's stuck in tissue. And it's really good for imaging gray-white contrast, right? Look at the detail. Head of the caudate, internal capsule, putamen, you can name any structure. So MRI is really the research, or the modality we use to do research because of its resolution. Okay, so what are the very basics of MRI? just want you to have a little background here, is that, we're mostly water, right? So MRI is great because it images hydrogen protons, which are abundant in water. So it's really the modality of choice for a number of reasons, including that. So what happens is that our hydrogen protons are oriented in different directions, spinning around like little magnets. When you put somebody in an MRI machine, what happens is they essentially get, there's magnetization there, and people's hydrogen protons then will line up in the main direction of the magnetic field, which from head to toe is called the Z direction. There's two other directions we'll discuss. The X is left to right and the Y is front to back. But in any case, what happens is we have this alignment of hydrogen protons. And what then happens is we use a radio frequency coil. So it's on the same band, similar band as the FM radio. And we're going to deliver radio frequency pulses to the person's head. Okay? So there's a couple of things I want you to know about that. The first is what's going to happen is we're going to move the hydrogen protons from where they are now in that orientation, slightly out of that orientation. And what's going to happen is as we do that, they're going to continue to release their energy back as they get back to where they were in the main magnetic field orientation. So that signal that is being released is recorded by an antenna in the MRI machine, and it is transformed into a digital signal. Now, the two key terms I want you to know are time of repetition and time of echo. Time of repetition is essentially how what number of seconds do we apply this stimulation that moves the hydrogen protons. And time of echo is when do we listen to hear that. Okay, based on those two parameters, it will decide what the image is going to look like. So so by changing those, we change the image. Okay, so I was mentioning the Z direction here, head to toe, right? That is the main direction of the field. And then, as I said, Y is front to back and X is left and right. This other property that the hydrogen protons have is called spin. And so we see that here. They are not just simply aligned in a field and stay straight, they wobble. Like if you spun a child's top, it would wobble like this and eventually fall down. This turns out to be important for another kind of signal we use in MRI that I'll show you in a minute. So there's going to be one called T2, that's this one, and one called T1 that I described a minute ago, and I'll define them more in a second. Okay, so what we said is that we have a main magnetic field. We have a coil to deliver radio frequency pulses, and it's going to move them from their orientation, and then we're going to listen as that energy is measured by an antenna in the coil. Okay? So the T1 image that I want to talk to you about first is where we move the hydrogen protons away from their main magnetic field, and we listen as they release their energy back. Okay? That's going to be really good at imaging fat. The next image, the next kind of image I want to talk to you about is the one where we're looking at that wobble, that signal kind of cohesion, and that is going to be what we're going to call the T2 image. Okay, before I get in, I don't need you to know the exact physics of these, but I just want you to understand the basic concept. But before we do, any questions? How was Thanksgiving, by the way? Everyone have a good time? I had a good time. We stayed home. Just relaxed. Okay, so with this signal that we're looking at here, the T1 weighted signal, what it is I mentioned, water will be imaged differently depending on what's surroundings. It could be pure water, it could be stuck in fat, it could be around, a lot of carbon. Whatever it is, it's going to influence that signal. So what we're looking at here are the relaxation times. So we stimulate with our radio frequency. And then what we do is we wait until a certain amount of signal gets measured by that coil. What we're going to do with this T1 is we're going to image when the signal is maximal for fat compared to water. That's why we see myelin really well. The white matter in the brain is fat, right? It's surrounded by fat, myelin. So we see it really well, and that's in contrast to the gray matter that doesn't have that myelin. Okay? But the main thing is we have sharp contrast here between gray and white. Okay. So the T2 image is kind of the negative of that, right? Now we're going to see that the fluid in the ventricles is bright instead of dark, and we're going to see that the white matter here, instead of being white, is now going to be dark. Why is that? This is a different kind of image where we really want a sharp contrast between water and white matter. So we do that in a similar way as we did the T1, controlling the TR and the TE. So what we see here is, now in this case, T2 imaging is about losing signal, but that doesn't really matter. The point is we have our image, if you will, taken at the time in which water is maximally responding compared to fat right here. And because of that, we're going to see water is going to be bright, and the rest of the signal will be somewhat darker. Okay? Okay. So I want to talk to you about the unit of measurement that we use in MRI. And it's called a voxel. So, you know, if you have your standard picture, you have 2 dimensions, length and width, and you don't have depth. Well, in MRI talk, what we have, because we have a whole brain in 3 dimensions, we have that extra thickness. So instead of calling it a pixel, we call it a voxel. That's all it is. It's a 3-dimensional pixel. And it's important because when we do research with MRI and other kinds of imaging modalities, we want to know how many voxels usually are activated, or how many voxels are showing a kind of pathology, or whatever it is. So literally, we want to know the number of them. By knowing the number and knowing the resolution of the scan, we can say that there is a volume of this amount, okay, of tissue that we're describing to you as the results. Okay. All right. Yes?
Could you tell us, like, about how big would a voxel be, and how does it vary based on the strength of the machine?
Sure, that's a good question. So voxels will be different for the different kind of modality. For this kind of image, this T1 image, it's always at this point going to be a maximum of 1 millimeter in that voxel. Now, we can get a scan that's less than that, but only in some parts of the brain. In other words, we'd be scanning, let's say, half the brain. If you want to scan the full brain, you're stuck with having about 1 millimeter voxels, which is still great, right? But if you want to image, let's say, the hippocampus only, you can get down to like a quarter. You can get down to like 0.25 millimeters. So it all depends on what you're looking at and how much time you have to do the scanning, would be the main thing I would say. And then with a T2 image, this type of T2 image here, a pure T2, it would be similar in the sense that we could look at the same resolution. However, as I mentioned here, most other kinds of imaging modalities in research use a kind of T2, okay? And we'll talk about different versions. So in doing that, we can't get that kind of resolution because the imaging is too complex. So we're lucky if we get 3 by 3 by 3 millimeters. We're happy with that. And you'll see why in a little bit, why some of those images are more complex. All right. So okay. So let's get into it now. What is functional neuroimaging? Well, we said that neuroimaging itself is mapping some kind of anatomical characteristic to a location. Functional neuroimaging is mapping some physiological characteristic to a specific location. Now I put PET up there, that's positron emission tomography. We don't use that for functional activation anymore, but when I was a PhD student, that's what I started out with because it was available, and MRI, fMRI, really, really good fMRI was just being developed. So it works basically on looking at glucose uptake, but it's not used anymore for functional activation because it requires exposure to radiation. So if you're one of those experiments, you've got to be willing to take a little radiation. fMRI, as we'll see, and all MRI does not involve radiation. It just involves magnetics and radio frequencies. So that's why we've moved to it, plus it has higher resolution. Now, PET is still used for ligand studies. In other words, let's say you're doing an Alzheimer's study. You could use PET also to look at how the ligand binds to amyloid in the brain. And you can look at that as saying someone has amyloid in their brain or not. But that's not what we're talking about here. So for the purposes of functional activation, PET has gone bye-bye. Right. Okay. So how does MRI, or in this case fMRI, work? It works based on sort of a complicated set of processes, but the basics are that what we're looking is at increased oxygenation in the region that is activated. So if you're doing a specific task like a memory task, you would expect to activate memory regions of the brain, regions that are involved in memory, compared to a control condition where you're doing something else. So this is just showing that low activity here, high activity in the task, oxygenated hemoglobin coming in, and that's moving deoxygenated hemoglobin out of the way. So we have this thing called the bold contrast that is that very process and is telling us what we're looking at. So we're not really looking at neural firing, but we're looking at a correlate, a strong correlate of neural firing, which is these hemodynamic patterns. All right, so how does it work? Functional MRI works basically by mapping physiology, right? Now, so what would be the task? Well, let's say you're an experimenter interested in memory and how it changes as we get older. So you might want to get functional activation maps of young adults and older adults, or even older adults over time, and see how their activation changes, right? So if you wanted to do that, what you're going to do is you're going to pre-train the subjects on the task. Because if they're doing a task, you want them to know exactly what they're doing when they get in the machine. Another thing is that we can't have people talking when they're in the machine. So we talk to them, but we ask them to press buttons to say yes or no, or to the task. Because if they move their head, they're talking, they start moving their head around, it's very difficult for us to get images, and our data suffers. Okay, so moving right along then, we see this person. They've been given a keypad and they're going to do some response. Yes is going to be one hand, or no is going to be the other hand, or one finger, or what have you. So we have to compare fMRI to control conditions. This could be, for example, reading words, and we're going to compare the memory task to reading words. We then basically, based on the physiology, we can assign statistical maps to regions of the brain that are active. So in this case, we see this massive activation in the left inferior prefrontal cortex for this task. We put the opposite contrast in cool regions, in blue regions. This would be more like looking at the words than remembering, which also could be of interest to a different investigator. Okay, so does that make sense? With fMRI, we're looking at doing a task, we're looking at mapping the activation in that task compared to some control condition that you think would be maybe similar, but it would take out maybe motor function or take out some other function, reading or what have you. So you could get the memory itself. So early proof of concept studies were studies where they just did things like this. You'd look at a checkerboard flashing, okay? And then another control condition, you would just look at the checkerboard, it wouldn't be flashing. So they were looking at visual motion, right? And we already know that V2 and V3 regions of the brain, as well as V1, everything we see here around in the sagittal slice here around the visual cortex is showing activation related to visual motion, as well as parts of the thalamus. So this study was kind of like, hey, this shows what we thought it should show. Seems valid, for this particular study. And there was a whole slew of studies to show that fMRI really is valid. So what have we learned from fMRI? So now I'm going to switch from the sort of technical things we've been discussing to more the conceptual findings and results. Before I do, any other questions? You going to make your professor ask all the questions here? All right, well, you just let me know. All right, so here's the things we're going to discuss, the main points that we have, what we have learned. The human brain shows functional plasticity, okay, can change. Regions can be used that are not being used for some other process. To compensate, teenagers do risky things because their brain circuits have not fully developed. The brain has an automatic default mode network. And fMRI is being used now, in some cases, for surgical planning. And we have those kind of studies going on here. They're patient-oriented studies, as we'll see, that inform the neurosurgeon about where to cut. And where not, more importantly, where not to cut. Okay, so this is one of the early experiments that looked at plasticity in the brain. And so what we see here is we see a sagittal image, right? And we see this activation pattern or region of interest in visual cortex. So that's where we all see things and put together shapes and stuff like that. This experiment was based on people who were either blind or sighted. So what you see here is in experiment 1, what they're doing is they're presenting auditory stimuli, so it's words being spoken. It's not obviously visual stimuli because the blind people can't see, but they can hear. So they're listening to these different stimuli, and what do you know that when it comes to sentences, the individuals who are blind show a big activation pattern here that is not seen in the sighted individuals. So it suggests that in people who are blind, the visual cortex, if it's not being used, it might be recruited to do something else. In this case, listening and making sense of words that are presented auditorily. Okay? And we see the same thing here when they added different other stimuli. The main point is when you compare nonsense type auditory to meaningful auditory, the visual cortex in those who are blind is doing something here. Okay? All right. This study kind of looked at how fast that whole process could happen, because you would think it would take years. But this study shows that it could happen over days. So what we're seeing here, we have sagittal slices over the brain, right? And here we see this activation in the visual cortex. It's small, but there it is. And so what happened in this experiment is there were individuals, subjects, who were sighted, they could see, and what happens is they got blindfolded for most of the day. This is day 1 when they're having this fMRI experiment, and we see what is happening when in this case with touch. So in this case, it's actually touch. So what's happening is the person's being touched at day 1, day 3, day 5, and day 6. And what's happening is they're actually showing activation over time, first nothing, but then they're showing activation in day 5 in the visual cortex. So this is a different example. In this case, visual cortex is taking up this touch stimulation because they're blindfolded and sight works with tactile stimulation. So that's pretty cool to see that this process can happen so quickly that we can take over different processes in primary regions where we thought they were not flexible. Yes?
Okay, so does that mean that if you're born blind that you have like higher activation than if you're like if you're blind over years, or is there like a cap at which like you can turn your auditory cortex into a visual cortex?
It's a good question. And so if we go back to this data here, what we see is that these are individuals who are blind, congenitally blind, right? So they grew up that way. And we don't know how long it took in this experiment for them to start to use visual cortex. This is a single cross-sectional study. For your question, which is a good question, you would do a longitudinal study. You'd get them at some younger age before maybe this was happening, and you'd see it become activated in these people over time. That's a great study. You should do it.
Okay.
Okay? That would be a great contribution to the literature. So, any other questions? All right, on we go. So the next thing I want to talk about is functional plasticity in aging. So now we're going to talk about just regular aging, normal older adults. There's no blindness or sensory deficits here that we're going to talk about. So we know that some studies I'll show you show that older adults show sort of different functional activation patterns than younger adults when they're doing the same task. So we want to understand why that is. Okay, so first of all, let's set the topic up by saying that one thing we see in aging that's very common is atrophy. So if you compare a 30-year-old to a 70-year-old, a 73-year-old, you're always going to see brain differences, right? These ventricles are enlarged because there's atrophy. We can see the atrophy in the enlargement of the sulci and the shrinking of the gyri compared to the younger adult, right? We can see the hippocampal shrinkage, ventricular enlargement in the inferior horn of the lateral ventricles. So we see a lot of changes that have occurred in older adults in the structure of their brain. So the reason I'm telling you this is because this suggests one reason why they have to compensate. They're compensating in a sense for brain that has atrophied and some cells have died. So how do they do that functionally? Okay, so this was an experiment that looked at this question, an early one, and what it's showing is that when you compare, this is a word pair recall task, so a cued recall. So you'd memorize words that go together, ball and painting, and then you would be showing one of the words in the fMRI scan, and you'd have to recall the word that it was paired with. So it's a verbal task, and almost all people are left hemisphere dominant for language tasks. So you see in younger adults that's the case. There is a left hemisphere dominant reaction in the inferior frontal region here in the thalamus, which is what you would expect. But in older adults, they show bilateral activation when they're doing the same task. So it suggests their brain function has changed somewhat. Maybe the left region, the region on the left isn't sufficient to carry out the task, so they need help from other regions of the brain. Okay, so that's an early example that suggested this could be compensatory, could be compensation. I show you this just to show you an example of some of the tasks that might be used in task-based fMRI. There's now such a thing called resting state fMRI, where you just have the scan where you're not doing anything. So when I say task-based fMRI, I'm talking about obviously doing an active task. And what we can see here is we can see this is task switching, this is working memory. So in the task switching task, what they have is different conditions. So you'd be making a decision on the shape. Is it a circle or a square? The color block, you'd be now informed, okay, you're making decisions on color. Is it blue or is it red? In the switch block, you don't know what's coming next. So it'll say shape, you have to make a decision, is that a square? You have to get the thing about color out of your mind now, because it's irrelevant, right? But then the next one may say color. Now all of a sudden you've got to suppress the shape and decide which color this is. So it's called task switching because you're switching between two tasks. And whenever anybody does that, they're slower in this switch block. But older adults show us even a higher amount, even greater slowing during this task compared to younger adults. And they do in most executive function tasks like this. So another kind of executive function is working memory. People know what working memory is? It's kind of like the memory you use, right, when we're actively solving something or keeping something in our mind, like a telephone number, something like that. And so working memory, we've done this task years ago where you just look at a pair of images and you're asked to memorize those, and then this will disappear, and you'll be asked for every individual stimulus, is it a match or a non-match? So that's an example of working memory because you got to keep these in mind while you're making your decisions. All right. So one study we did a while ago looked at this. So when we have older adults showing differences in activation compared to younger adults, we don't know is it compensatory or not. In other words, is it helping them? It might just be a malfunctioning sort of situation, right? Where they're showing activation in another region, but it's not helping them. But what we want to know is it helping them? So the way you do that is you correlate it with behavioral performance, right? We want to know, is it helping their performance? So this was a study where we looked at functional connectivity. So you could just think of looking at, let's say, two regions, the posterior occipital region, and asking what is their relationship over time? Are they correlated, those activation patterns, or are they not correlated? So with functional connectivity, you're saying, what is their correlation score, if you will? And that's what we have here. We have correlation between regions. So that's their connectivity profile. So what this study showed is that a high connectivity between these regions for younger adults didn't help them at all. You see these open circles here. There's no relationship. But for older adults, in the black circles, there is. So you can see that the higher the connectivity, the faster the response time seemed to be. So we want to be fast, right? Accurate and fast. So that is a suggestion that this network is helping older adults, that it's compensatory, because it's actually improving the performance in those who use it. Does that make sense? Okay. Okay. So now I want to talk a little bit about teenagers and risky decisions. Do we have any freshmen in the class? I don't want to single anybody out, but we've all been there, right? And so everybody's probably heard now about the developing brain and how it's not exactly developed until you're probably in your early 20s and so on. And there is evidence to support that. In fact, it was presented at the Supreme Court years ago for support of the idea that teenagers don't receive the same sentence when they commit the same crime as an adult. So one of the interesting fMRI studies was that we know in general when we're dealing with risky situations, we try to put the brakes on and stop that riskiness when we're adults using the inferior frontal gyrus and the anterior cingulate cortex. So you see the corpus callosum here, just above that is the anterior cingulate cortex. And so activating those regions in people who are adults goes along usually with making a decision to stop a risky behavior. So for example, they would show images in this experiment of people making risky decisions, and you'd be sort of having to say whether you agree with doing it or not, like run a red light if it just turned red, right? Or do something like that. So in adults, what you see is they have a strong activation pattern to that situation in those regions of the brain, presumably because they're putting on the brakes. Whereas in teenagers, you don't see that. You see a smaller response. So it's more like, let's run that red light and not worry about it, right? Yes?
This is on the previous slide, if you can go back to it.
Sure.
Okay, so for areas of the brain that are kind of like unilateral, I guess like speech and language, where it's just like the left side, would adults also have an activation like that versus kids, or is it just one?
So this here, okay, so your question is a good one. You're asking about language tasks, which we know in almost all people are left lateralized. So you're asking in a way, would there be a difference in connectivity between younger and older? So you're absolutely right, language tasks are left lateralized, but there's still frontal activation on the other side as well. It's kind of related to other parts of language, like prosody, and not so much language, gestural things and stuff. So that study's probably been done. I don't know the answer, but I would suspect that if there was some decision to be made and you had performance, right? So you would correlate your performance with that connectivity. It'd be interesting. I think it would probably still be the case in older adults that they may be helped by that. But it's true. It makes it trickier to do connectivity studies in a very lateralized task. So, all right-handed people are left hemisphere dominant for language, but most left-handed people are also left hemisphere dominant for language. That gets misstated sometimes. About 60% left-handers are very few. They're 1 in 10, and 60% of them still show left lateralized language, but about 40% of them are flipped, where their language is on the right side. But that's very rare, but it happens. That's why when people do research and they do verbal tasks, language tasks, they will almost always say all subjects were strongly right-handed. That's why they're saying that. Because they're saying we would expect the activations in the classical regions of Broca's and Wernicke's on the left.
Thank you.
You're welcome. Any other questions? Nope. Okay. Right, so we were doing the risky decisions. People get that idea. Putting on the brakes is harder for teenagers than adults. Although teenagers can drive at like 16, right? So I have 2 daughters, and the younger one is now 16. So she drives when we drive to school. It's terrifying. Every day I feel like we're going to be in a bad accident. So I have that sticker, though, I put on the bumper that says, please be patient, student driver. And that really works. Really works. Like even the biggest jerks on the road, they see that and they're like, oh, okay. They go in the other lane or they slow down. I forget to take it off sometimes. Excuse me. And then it's like someone pulls up next to me and says, why does this guy have, is he just learning to drive now? He's kind of old. Okay, so then what we're going to talk about now is the default mode network. So this was actually discovered very close to where I did in a lab where I did my postdoc at Washington University, and it's now become the most famous network ever known. So it's the network that we use when we're kind of just going about our day. We're not asked to do take a test or answer a hard question. We're just going about our day, driving home, thinking about what the day. So this activates a characteristic set of regions in the brain that are medial frontal and parietal, and they show reduced activation during a task. But when you're not doing a task, you're just resting, they show very strong activation. So it's internally directed thought, if that makes sense. So what is and so the default mode network is predominantly a medial network. It does have lateral parietal on each side, but the regions that are the most central are the frontal pole and the parietal, midline parietal. We call this region the precuneus because it's just before the cuneus. Okay, so that's what we're doing when we're using the default. We're kind of left to our own. We're thinking about the past. We are thinking about oneself or others, thinking about thinking about the day, going through the day. When you lie down and go to bed, you start thinking, reviewing the day. So that's another example. Okay, so remarkably, not only is this network seen in apes, but it is seen in adults during sleep, anesthesia, and even minimally conscious states. When someone's in a sort of a coma, they are still showing activation in this region. So it's a very old and very powerful network. Okay. All right. So we'll end off talking here about neurosurgical planning. So, neurosurgeons always have that dilemma. There's a tumor, and they have to deal with it, but they don't want to cut out viable tissue, right? They want to cut out the tumor, but basically not damage cognitive function if at all possible. So that's not an easy thing to do, and this is sort of something that's still being perfected, but it is used. And so let's just use this example here of the foot region and motor cortex. So if we look at our homunculus, you guys have seen the homunculus before of sensory and motor function, and we see that the feet are medial, right? So they're medially oriented, and then we go up toward the face in both sensory and motor function. Now let's just remind ourselves that sensory motor function here happens in the sensory cortex, and then a motor function happens in this strip called the motor cortex. They're adjacent, right? Okay. So going back to this, then the surgeon has this individual, this patient who's doing an fMRI task that's going to be related to moving the foot. And what is seen here is pretty messy, right? Because the white here represents, like if you see here, the white here is the tumor, right? You see white here, you see it here. But it's kind of intertwined with regions of the brain that are still showing viable response, still showing metabolic response. So as a surgeon, he or she is left with that very tricky work to do about what they're going to do, how they're going to advise the person, and what their plan is. So fMRI can be helpful in that regard because you just don't cut out all the region without figuring out what's going on there. So I think that's it. Some limitations of fMRI. It can't tell us if regions activated are inhibitory or excitatory, right? It's very intensive, involves a lot of analyses, and a bunch of other things here related to really measuring hemodynamic signal rather than neural signal. We have to make sure fMRI maps are not corrupted by motion, and a lot of statistical comparisons. So it's still primarily a research technique and not a clinical technique, but it's being used more and more for clinical cases. So this is just a summary of what we've learned. So these are the topics I covered, and go ahead and go over those. And if you have any questions, please feel free to reach out. So that is it. Thank you.
I had one more thing I forgot to mention at the beginning of the class. When we go to the MRI, if you have any implanted medical devices, you need to let me know. It's not very common in people your age. It's more like pacemakers and things like that. For things like insulin pumps, you might have to turn them off while you're actually in the facility, but usually that's not a problem for most people. Things like screws or like stainless steel screws in your body or something like that, those are okay. Glasses, okay. Piercings are okay. Anything like that is not a problem. It's more like large metal plates in your head, or interestingly, if you did welding, because welders get little splinters of metal especially in their eyes. That can cause a problem. But yeah, if you have any of that sort of thing, let me know.
And there's a technician there too, as you know, who will make sure that no one goes in the actual MRI room. You can be in the control room. You have to just do this training to go in different parts of the center, but it's a fun visit, I think.
We will. So we will be going over into the room. We can't take very much since it is a pretty tight room. The control room is. So we won't be taking our stuff over there with us. You will have to leave in your computers and stuff in the lab downstairs, and I can lock that room. But just so you know, you'll have to leave stuff here. You'll be able to take your coats, but you might want to leave any electronic devices back with your backpacks and such. All right. Well, I'll see you guys this week. It's a fun trip, and like I said in the email, it's worth about $2,500. I think. I'll see you in this room. See ya. Thanks. Thank you so much. Sure, yeah. Yeah, absolutely. Send me an email. Send me an email about it yet? Send me an email about it. If you have your
we did a lot of
so we'll have cards. Yeah, I can send you.
Actually, I think the same thing.
When you send me that information, I'll send you back.
Actually, it made him my right foot there. I just
I'm sorry, he's got it.
You can tell me if you know nothing about it.
Sure.
My mom had it.
Yeah.
3 people might have it.
Yeah. Okay.
Because I can learn how.
I do not
When
know.
you said something about screw, I almost looked over
You
at
might-
I was like, I know that's something.
You might want to ask when you get over to the MRI facility.
What an MRI showed that there was like
That, yeah.
Because I'm taking a protein share right now.
Okay. Yeah.
Taking a lecture for.
Yeah. Yeah.
physics project.
Oh,
Okay. Well, I mean, some people, yeah.
It's just because she was like,
One of the girls was went through and did it for free.
I'm
It's like
not
a physics guy.
No, I totally understand. Yeah. What did you say it was again?
So you just had to phone that.
I don't know if I'm saying it. But I do it.
Okay.
Like, this is the first
So,
time I'm like,
okay.
that.
Okay. Yeah, I don't know that one. I didn't get, so in, I took neuroanatomy for grad school, but it was mainly focused on like kind of standard neuroanatomy and and not so much on the pathology. So I didn't go, yeah, I didn't get as much of the pathology stuff when I was in it, except for Alzheimer's and Parkinson's. It's been a while on that.
That's for
but yeah,
Parkinson's.
yeah.
All right, thanks.
Titanium good
What's that?
for MRI?
Titanium's fine, yeah, because it's
I
non-magnetic.
didn't think so.
Um,
Yeah, I got my whole collectivity. It's just a lot.
Oh, wow.
Inside the bone.
Yeah. You might want to tell them that, but it shouldn't be a problem.
Yeah.
Yeah.